Now, a first step in building up this mathematics is to learn how to deal with this type of an integral. Now, this type of an integral has a special name. It is known as the Fourier transform. And in our course, we have students who enter who are very familiar with the Fourier transform, and we have other students who enter who haven't seen it before. So what I'd like to do is I'd like to make this course as completely mathematically self-contained as possible. So we will actually be reviewing all of the mathematics behind the Fourier transform. On the other hand, or at least from the practical side, not the theoretical math, but on the other hand, for those students who are familiar with the Fourier transform or these new mathematical concepts, I'd like to always present them from a different perspective to give you perhaps more perspective on the mathematical operations so that you too can carry away something from this course. So what I'm going to describe to you now is the physicist's view. The physicist's view of the Fourier transform. And by Fourier transform, what we mean again are these types of integrals. Now, the physicist's view of the Fourier transform that I'm going to show you, this actually comes from Dirac. And this is actually in his book on quantum mechanics. So the physicist's view of this actually comes down to a principle due to Dirac, which is known as the quantum principle of superposition. Or if we would like to abbreviate it to save on writing on the board, we would call this QPS. And the quantum principle of superposition, it actually isn't something new. It comes from our statement of the de Broglie hypothesis. And this deals with the part where de Broglie says something along the lines of where we can calculate probabilities as proportional to the square of complex amplitudes, where those complex amplitudes are written as a superposition of something, right? And we had said that these somethings behave a lot like waves, but more generically, it's just a superposition of something. So if I were to give a definition for this quantum principle, the definition would go something like this. It is the physical sense. So I'm talking about something that has to do with the universe, not necessarily just a mathematical statement. So the quantum principle of superposition is the physical sense in which any generic quantum state of a system, right? Because a given system can be in any kind of a quantum state. I can create practically, any state that I might like. But if I am in such a state, there's a physical sense in which that generic quantum state of a system, it can be written as a superposition of something. As a superposition. Oh, actually, I don't want to phrase it as superposition, right? I'll put it this way. It's the same idea as a superposition. I'll write it as a superposition mathematically later. I just want to say, sort of in physical terms, in which any generic quantum state of a system contains within it, right? Contains within it, and here, I'm sorry that my writing got a little bad. Any quantum system contains within it the pure states corresponding to outcomes, particular values, theta naught, of observations of an observable O. So here's the idea. I have a system in some kind of generic quantum state, right? and I go and I observe one of my observables. And as we know, the result of doing that is always a pure quantum state with respect to that observable, a value associated with the value that you found when you made the observation. So these pure quantum states somehow come out of the initial generic quantum state that my system may have been in. So what we're saying is that for that initial state to somehow be able to yield us upon measurement these pure states must somehow be contained within the initial state of my system. So maybe I'll make it any initial quantum state. Right? What the measurement process does, apparently, right, is it's a filter. It filters out all of the other pure states of the system and leaves me just with a single pure state. Now, I won't know what that single pure state is that I'm going to get. Which one I get is random, fundamentally. That's undergirding all of our quantum mechanics. But nonetheless, those states that I yield upon those observations or those measurements must somehow be contained within the initial generic quantum state of my system. So, this is just a general physical principle. They had to come from somewhere, so they come from the state of my system. Now we have a symbolic way of writing this, which will help us and simplify our notation quite a lot and save a lot of writing on the blackboard later. So symbolically, the way we would denote this principle is we denote any quantum state that you want, we denote by this symbol with a vertical bar and a greater than sign. And there's a name for this system, so this is called a ket, K-E-T. And the term ket, K-E-T, my pen is giving me a little trouble today. The term ket comes actually from the term bracket, right? And we will get to the brack part later of bracket, right? But this is the ket part, and this represents some initial generic, right? It doesn't have to be special. It doesn't have to be a pure state. Some initial generic state of my system. Now, my initial quantum state of my system, actually this represents any quantum state, represents any quantum state. That's probably a better way to say what the ket does, represents any quantum state. Now, we're going to give a name to this state. It could be, Joe or Bob or Sally, right? We can call it whatever we want so we know which state we're talking about. For the initial generic state of my system, I'll be a little more mathematical. I'm going to call it psi. So this is my initial generic quantum state that I was thinking about. Now, what Dirac is saying, right, is there's a principle of superposition. So what he's saying is that this initial state can be written just like de Broglie is telling us as a sum of some other things. And what Dirac is saying is that those other things that must be contained within my initial state are actually other quantum states, but these are other special quantum states. These are the pure states of my observable with a particular value. So what this represents then are pure states of O, or pure states with respect to O, right, with different values. And this one that I've drawn for you is the one that has value O naught, right? And then not O naught, I'm going to call it O sub n because there can be different pure states that I'm summing together to get my final state. Now, the last piece of this idea is that these states can come with different weights, right? There might be a state that you just don't have in your superposition, and then we would associate a zero weight with respect to it. Or we could associate other states. So these are weights, and these weights we would suspect are related to the probabilities of finding the different values. On, right? So that would be the probability P of On. That is what these weights actually are related to. Like so. Now, of course, we don't know what this relationship is, but we expect, well, if there's zero weight and it's not contained in my initial state, there's no way I will observe that observable. So zero probability should correspond to zero weight. And also we would expect then that a very large weight would correspond to something with a rather large probability. So this is the generic idea from Dirac of the quantum principle of superposition.